Hello, a very good morning to one and all. I'm Praveen Kumar. I'm currently studying final year of BTech. So today we are going to see a time series analytical API, which is very important real world modern software applications where data is released in millions in telemetry, and we need to process the whole data and also getting the database rollbacks. I mean, we need to get the hourly aggregations, the and daily rollbacks and data retention. Once we process the data, we need to delete that raw data. So everything where data is really a primary axis of time, so time plays a key role. We need to build that system. So this is not just a simple system which queries the database and prints the final count using something methods like in SQL like count. No, here we are using pre-computed rollbacks and mastering sliding window and also scheduling the jobs. I mean, cron shop schedulers using app schedulers, advanced Python schedulers. So yeah, let us take a look at everything. So you can access this project with the URL github.com Sachana Praveen Kumar and time series analytic API. Okay, features. What other features we have implemented is event ingestion with payload validation. So a user can send the data with metadata like null. So we don't need to calculate the null values for the dashboard summary and reduce back to sliding window. Suppose our API is get into abusing, for example, a DOS attack, denial of service attack, or a hacker bot will try to abuse our API with nearly 200 or 300 requests per second or per minute. So we don't want to consume our resources and computation. So we are just implementing the sliding window rate limiting. So I will also show you the math behind that and time series analytics with real-time and historical query routing. So with real-time data, for example, we need to get the data within the previous hour, and historical query rating means we want to get the data which is 30 days before, and cached database summary responses, because every time we don't need to hit the database and make the heavy lifting math behind the hood. So just we are storing the data, the main frequently accessed data, we are storing it inside the memory, which is our ultra fast nothing but RAM. Background jobs for hourly rollups, daily rollups, and retention cleaning. Retention cleaning is nothing but we don't want to store the raw data once processed into the and summarize. We don't need to store that raw data, just we are just cleaning the data. So this is the high level architecture of our system. So yeah, the purpose of each module. App scheduler will do the hourly rollup and daily rollup and data retention cleanup on PostgreSQL. The client, which are who are sending requests, the fast API. Suppose we need to send the data to server, we will use the post request, and to get the analytics and the dashboard summary, we are just using something called Redis. If it is cache hit, we will be serving the data from Redis. If the cache is miss, we are serving the data from PostgreSQL. So another endpoint for health of the application. So the tech stack, I have used Python 3.11 plus and Fast API because it supports async native programming, and also useful for building high performance APIs inside the microservices or anything. PostgreSQL, as it supports something like upsets, do conflict and update when raised in update, and Redis, nothing but to store the frequently accessed data, and async PG, which is our nothing but a Python based SQL adapter to communicate with the database, and AP scheduler for scheduling the jobs, PyTest for testing. So Docker and Docker Compose for containerizing the application. So this is our project structure. And make sure you have installed Docker and Compose in your system to run this application. You can simply clone my application and test it well. So yeah, let's get into the some advanced concepts behind this. So yeah, building a time series analytical backend is not simple as dumping records into we're just using insert command and count command to fetch the data. But what happens if you have millions of rows to fetch the data? So that's why we are using pre-computed aggregations, which are nothing but rollups and intelligent query routing, caching layers, and background processing mechanisms. So what are the problems we may face is unexpectedly slow, blocking database resources and degrading the usage experience. So we don't want to make our application in a synchronous way, which can be block the complete system for processing a request or a process. So yeah, key concepts we are using time series data modeling. So within the time range, we are making the data and data rollups, aggregations. For example, hourly rollups, hourly and daily rollups. So which is a key pattern in data engineering. And idempotency in distributed system. So you know background jobs can fail sometimes, timeout or restarted. So we need to design the system idempotent, meaning they can run multiple times for the same time window counters, and implemented a more robust sliding window algorithm. Plus it should not produce a duplicate data or corrupting final metrics. Yeah, as mentioned, I have used sliding window to prevent our API from abuse, and query optimization and caching. So just I have mentioned we need to develop a system that is high throughput. Means how much of data throughput means how much of data transferred per second. It will be measured in MBs or KBs. But latency is how long does it take to process? I mean, send a network packet from sender to receiver. So latency will be helpful for calculating the how long, how much time, and throughput, how much data has been transferred per second. So as you know, we need to design high throughput ingestion. So we need to send more data, and to read the data, we need to take less time. That is called low latency querying and serving a powerful additional to backend. So this is simply our diagram I have shown in your GitHub. So let us get into this series API. So yeah, let's start with the infrastructure, which is our nothing but Docker. I have created some services like database, which will be using the image from Postgres 15, and make sure that you will be using volumes, because whenever Docker sees something like .sql files, it will be storing in this place and runs the SQL. I have checked and Redis for caching. It will be downloaded using the image Redis 7 Alpine. So we don't want to install in our system. We want to install inside the container and the API, which will be using this source code as an image and builds the API. Okay, these are the tests and Docker file. You know, this container will be the API container will be using this image to build, and requirements, as you know, the fast API framework, and it's just a web framework. It does not know how to handle the request. It will be handling the request to the web server or nothing but UVCon. It runs on the ASEA server, which is our asynchronous server. It is async PZ, which is our Postgres to Python communicator, and pedantic were data validation and payload. So when the request hits the API, we need to validate the data, whether all the fields are in correct data type or not. Redis, as you know, for caching, and .env for reading the environmental variables, and app scheduler for for job scheduling, and PyTest HTTPX are nothing for testing frameworks useful. So I have used something technique called database connection pooling. Why I have used it? Because opening a database connection for each request will make our application slower. And if thousand users are hitting the request at the same time, the Postgres unable to process the data, because it's something have maximum connection limit. It may be around thousand or something. So I will be using async context manager because all the above code will be run when the server boots up, and the yield after this code will be run after the this code will be run all this code will be run when the server is able to, I mean, when the docker is going to close. When you are kill the server, it will be run. So health status, and in events endpoint to ingest the data, the client will be sending the data, the raw data. It will be stored, and we'll be implementing. Okay, let's get into start from the models, the schema, our database design schema. So the raw events, the user will be sending this data ID. We will be using primary key, and default we are just generating the id with uuid, universal unique identifier, and the event time. For example, an event type can be a page view, a button click, or like that. The timestamp, here you can see the timestamp data type is timestamp tz, which is our time zone also included, and the constraint is not null, and metadata is our json binary. So if we are can using something like metadata like the page URL, the amount of time spent by the user, something all will be stored in this metadata. And we are using something called indexing because indexing makes the query performance faster, because we don't want to check every row and scan the database. Making indexing, we can simply just go to that row and pick the data. It's like simply a textbook. When you want to see the concept of something, you don't need to scan every pages, but looking at the in front of the index, you can simply go to that page and read the concept. So just now we are indexing on timestamp, and we are using this in sorting order, descending order, and another index on raw events. Indexing, under the hood, it uses something called b plus trees, a data structure, and for hourly statistics and daily statistics. So I think you have observed that primary key, bucket type, and event type. For example, there are different users hitting the same API and that exact millisecond, and both their event type is page view. We don't want to crash the API. So instead, we are creating a primary key for each user. So it will be differentiated. For example, a user uses this API at 2:30, and another uses at a 2:35. We don't need to crash that. Just we are overriding the count. For example, one, and here also one. We are just incrementing the count. And same for the daily statistics. This is the models, and event payload checking. I mean, we are validating the data before it enters the API. And the event type maximum length would be one, and maximum length is 50. For example, event type can be a page view, button click, like that. Timestamp. So we are just not only using the date time, we are also using its time zone. UTC it will be used, universal time coordinator, and metadata we can set it as optional. It will be returning a dictionary, which is a key type of string, and value can be of anything. So there are difference between default and default factory. So default can be used for static values only. If we are using just default equal to some server time, the server will store for every request that exact time is started. Default factory for dynamic values, for each request it will be changed. That's it. And so in order to ingest the data, we are writing the queries, and we have here we are using something called SQL injection attacks. If something values the user value, the user can type something. If the condition is true, the database will be accessed. So that's not we are using. There's something called using SQL injection, and this is an asynchronous programming. We must define our function with async, and await can be used only if there is the method signature is async. Async will be helpful for in event loop. because it will be single threaded, one request at a time. Await makes us to wait, and event loop will be handling another task until this is computing, because it has to execute from the database. It nearly take 2 to 3 milliseconds. So we are just sending the query and the payload dot event type and payload dot event timestamp and the metadata as JSON. So once it is stored, we will be returning status, success, and event recorded. So as I mentioned, I have used this database connection pooling. So yeah, we are be creating a pool and with the database URL, and for Redis also we are creating a pool, not pool. For Redis we are not creating any pool, just we are using from the URL. And you can see decode responses equal to true means Redis will store the data in bytes, and we need to again decode the data. We can be using dot decode, but using decode responses will be helpful and makes faster. So we are just taking a connection pool from the database with app.db.stable. Okay, you can see something called dependencies. We are injecting the dependency, which is our check rate limit, which is defined in the utils.rate limit by. So as I mentioned, we don't want to use fixed window. For example, some tutorials will say fixed window. Window will makes application slower because it is saying at exact, for example, take an example at 12 o'clock exact 0 minutes, a user can send, a hacker can send 200 requests. Okay, it will be handling the 200 request within the minute. Once it's completed, it will be moving to another window at 12 o'clock. It will makes the hacker can send another 200 requests. So this will make nearly 400 requests within the minute. So we don't want to make in that way. Instead, we are using sliding window protocol. It will check the request which are less than 60 seconds ago. So we don't want the request to be processed within the 60 seconds ago, which will be helpful for saving our RAM and computation. So here I was using Redis, and based on the client address, this is for testing only if request.client else 127.01, because we are using fake browser for testing, and the Redis key will be setting as rate limit and the client IP. So we are exactly converting into numerical value. The time will be written in seconds and will be converted into milliseconds. And window start, how many seconds within the previous 60 seconds. And the request ID, we are just appending our client IP with an unique ID. So pipeline, which is nothing but transactional pipeline for Redis. So there will be mainly four methods in the pipeline. One is jet remove range by score, the key we are sending, and the zero and the window start. So within the previous 60 seconds, how many requests are there, and z.add request id dot no. So current request will be added to the pipeline, and jet card and expire. So we'll be deleting all the request within the previous 60 seconds. So again, we are using await because the network has to done all these four methods. Instead, we can use a normal one, but it will be synchronized. So pipeline will be helpful to all these messages, tag these messages in a queue and pass over the network as a packet. So request count, how many requests has been there inside this. So we'll be storing that in the results. So result of zero will be helpful for remaining range by score, and at a index number one, there will be stored the added request, and at a two, how many requests are there. So just we are sending, if the request count is greater than or equal to 200, so we are just simply say within the previous seconds there are more than 200 requests. So we can say to status code to 429, and the detail will be too many requests. So that's how we have implemented the rate limiter. So this will be for ingesting the events into raw data, events table, and analytics. So you want to get something like analytics, for example, a window date, start date and end date, how many requests has been, how many events has been done. So everything will be stored in this analytics. And the dashboard summary, for example, a 24 hours dashboard summary we will be storing in the cache. For example, we are setting the cache key as a dashboard summary 24 hours. If the data is available in the cache, we will be serving from the Redis and returning cache data is true or not. If I mean the time has been exceeded, we are just executing the database query. So event type and the sum of event count, how many events are there, as 20 last 24 count. So this is an SQL query for querying the 24 hours data. And just we are using await, we don't want to process this only. It will take some time until unless you can make your work. And the metrics are stored in the metrics variable. And not only checking from the data, we are setting, I mean we are adding that data into Redis. For example, another request can use this Redis data and simply return the data to the user instead of carrying the database. So this will be helpful in applications like Twitter. So when you want to fetch the data from last 24 hours, you can simply fetch from the, not 24 second, in a day, the last minute. If the data is available in the cache, you can serve it, or we can serve from the database. And not only serving from the data, we are writing to the cache. So that's it, I think. So the aggregations are an hourly roll up. We are not only running for hour, for every minute, 5 minutes we are calculating. And as you know, you have a doubt something like why I have written minutes equal to 10 for run daily roll up. So for example, we want to get the near time analytics. For example, in a day, the manager asked how many requests have been done in today morning shift. So we will be running at midnight 12 o'clock. We will be getting the older data. So that's why for every 10 minutes also we are running this daily roll up. And data retention means just we are clearing the data from the past 30 days. So that's the one. So these are helpful for fetching hourly analytics. Yeah, this is for our hourly roll up and daily roll up. And data retention, we are using delete command. So that's it. A practical demonstration. Okay, let's run this application in our system. So everything is built on my side. So I'm just starting the containers. You need to use something called hyphen hyphen build to run on your system. So yeah, just I'm ingesting a data with event type as page view and the metadata something like URL, which type of URL. So yeah, the message has been stored in the database. And you can also access this interactive documentation with the Swagger UI, which is defaultly given by the Fast API. You can hit this endpoint and you can get all this data. So let us check the help. So yeah, status okay, database connected, okay, everything is running. Suppose we want to get the date is 12. So suppose we want to get the today's data. Okay, let us get the dashboard summary. So these are the data. Just right now, we have created this page view, and this benchmark test. All this 199 has been done taken from the previous data. So I have tested it on my side before because Docker uses something called volumes. It will be storing the data in the volumes. We are getting that type of data. Get slash analytics. So that's it. How I build this type around performance time series analytical API, and let us see the submission. So these are the necessary commands to run my application. Okay, let's run the benchmark. So this will be helpful for something like is everything working, not how much of time is taking for each thing. Yeah, I think everything is idempotency means. So just we are don't want to get the duplicate data for every time we are getting the API, hitting the API. We just need the reliable data. Okay, something it's under the scripts folder. So yeah, you can see the average latency as 0.0277 seconds. So how long it's taking time for processing the request. And our sliding window protocol, I mean, sliding load test has been 199 has been accepted, and 51 request has been rejected because of too many requests, and rate limiter successfully defended the API. So yeah, every query was run in time, and let us run some tests also. Let us look at the test cases I have written for missing payload and invalid routing, and testing background worker. So you can see the total test says 88 percentage. So that's it, guys. How I implemented the time series, high performance time series analytical API with fast API and other some tools. So that's it. Thank you. Comment if you have any doubts.